Before I jump into this topic, let me tell you a few words about myself. Since I wouldn't consider myself an ML researcher, I do theory of computer science, not necessarily theory of machine learning. Part of my research could be considered, let's say, related to machine learning, but definitely not the main part of it. So I wanted to present somehow to you what are the topics of my research. And I heard that nowadays, like, you're almost obliged to talk about language models, so I decided to use a language model to do that. So I downloaded from archive abstracts of all my papers. And I also downloaded a universal sentence encoder. It's a language model. It takes as an input some sequence of words and outputs just a 500-dimensional vector that represents the content of the thing that you gave to it. It's designed to work with sentences, but I fed it with abstracts, so it's like a couple of sentences, but let's say it's still a reasonable use case. So after doing it, I got, like, for each of my papers, I got like a 500 numbers that were hopefully representing the content of this paper, or at least the abstract. And then, well, then I just run a clustering on these vectors so that it groups my papers into several, like, groups of papers on a similar topic. And to present it to you somehow visually, I also run a dimensionality reduction, so from 500 dimensions down to 2 using PCA. So now I can really plot it on a slide. That's the plotting code. And, well, this is what I got. So I think it's like amazing scientific progress that we can do such things right now, but also amazing technological progress that me, having zero experience with language models, I could write this like 10 lines or something of Python code and in 1 hour produce such a plot. Okay, to be honest, after 1 hour I got like some version of this plot, but to make it look nice, I spent another, let's say, 2 hours. But let's forget about it. Okay, no more about language models because I don't know anything more. Something about these papers of mine. This biggest group is fine-grained complexity. So I'm trying to figure out how fast you can solve particular problems. So for example, this kind of sequence comparison, do you really need quadratic time to do that, or can it be faster? Is it just that we haven't found a good algorithm, or do we have some like reasons that it's probably impossible? So this is main part of my work. I'm not going to talk about it today. The second big cluster is what's called algorithms with predictions. This is more related to machine learning, but for me it's still pretty much theory. And then there is a couple of outliers. And then there is this outlier in the middle, which is about explainable clustering, and that's the topic of my today's talk. So, clustering can be hard to explain. What I mean by that is that, for example, if you run k-means, then these things separating clusters from each other are just hyperplanes in high-dimensional space. So if you ask a question, why this point is in this cluster, then the answer is because it satisfies a number of linear inequalities. So if you're, for example, classifying people into various categories of risk of some disease, then you may end up with an explanation that this person was classified into this group because, well, something like this. It's really hard to make sense, for us at least, of such a classification. What is much easier to understand, for humans at least, is decision trees. So, for example, you could say that this person went into this group because their weight was over 100 kilos, they're more than 90 years old, and they're unvaccinated. This is something I can understand, what this group of people consists of. And such a tree defines a clustering, right? Each leaf of this tree defines some part of the input space. Okay, so I will call this a threshold tree. So a threshold is a binary tree. In each node, internal node, I have a threshold cut. So one feature, and I look at one feature, there is some threshold value. If it's smaller, I go to the left. If it's larger, I go to the right. And then if a clustering is given by such a tree, then I call it explainable clustering. So I have a tree with k leaves, and I split my space into k clusters. So this is easier to understand, but not every clustering can be produced with such a tree. So probably the clustering that I get is worse than the unconstrained optimal clustering. So the question is how much worse it is. How much I have to pay in terms of my clustering objective, whatever I was minimizing, to get explainable clustering. This is one question. Another reasonable question is, can I find such a good explainable clustering? And of course, people are working on all sorts of explainable models, also for clustering. It's not a new topic, but this particular, let's say, formal phrasing of this problem, it was proposed in 2020 by Moshkovitz, Dasgupta, Rashtchian, and Frost. What would be they also proposed, like they defined the problem and proposed some approach to it. So to make things more precise, let me focus in this talk on k-medians. There are like various clustering objectives, k-means, k-centers, k-medians, etc. For k-medians, kind of the math is the easiest, so I will focus on it. But all these things also work with different bounds for other clustering objectives. So my input is a set of points in d-dimensional space. I measure the distance by L1 norm. So basically the distance between 2 points is the sum of differences over all the features. And now I want to find k centers, so k points in this space, assign points to these centers, and minimize the total distance between points and their centers. So since we're in L1 space, then basically the value that I'm optimizing is the sum of lengths of these segments that go from, like axis-aligned segments that go from points to clusters. And as you can probably imagine, since in explainable clustering, we're cutting aligned to the axis, this objective makes it easier to analyze than, for example, if you were in L2 norm and these lines were diagonal. Okay, and the general approach, honestly the only approach I know for producing an explainable clustering, is to start with an optimal or close to optimal unconstrained clustering, and then kind of modify to make it explainable. So I start with a clustering. These stars are centers, the dots are my data points, and I want to modify it to be explainable. So reassign some points to some centers such that this clustering is given by a threshold tree. And the way I'm going to do this is I'm going to put these threshold cuts until in each cluster I have only one center. So at first I have like everything, nothing is split, so all my centers are in a single cluster. I do a cut. On the left side I have only one center, so I don't need to split this part anymore. And on the right side I have two centers, so now I do next cut and split these two centers. And at this point I got some explainable clustering. Several points were, this point and this point were reassigned from one center to the other. So I lost something in my objective value. Okay, and what was the first algorithm proposed for this problem? Well, whenever you make a cut, you pick a minimum cut. So a cut that makes the least number of points go to some other center. Uh, yep. So looking at this example again, as you can see, there is no cut that would not separate any point from its original center, but there is a cut that separates only one point, this cut. And then again, here on this side, there is no cut that would not separate any point, but there is a cut that separates only one point. So this is a mini cut. And this is how this algorithm works. What's the idea behind the analysis? Well, they showed that the first cut you make, the number of points that get separated times the distance from any point to the furthest center is at most the optimum value of the whole clustering. So when you separate a point from a center, you do not know what will be its final center. You just know it won't be the best one, the original one. But we're estimating here it in a pessimistic way. We assume it will go to the furthest one. So from this point on, we can forget about this point. We already counted like the worst case scenario for it. And it turns out that the single cut gives you, like, increases this cost by at most opt. Then there is some points left on the left side, some points left on the right side, and it turns out that the optimal values for these points are at most the total optimum. This is because when we put a point on the wrong side of the cut, we're already like overestimating its cost, so we can forget about it. So now in these two sub-problems that were left, we have only points that are on the like good side, so they still have connection to their clusters. And this is true for every level of this tree. So the cost increase at each level is at most optimum, which means that the price of explainability is at most height of this tree. So if the height of this tree is h, then what you pay is at most h times opt. Now the height can be upper bounded trivially by k. If you have a tree with k leaves, the height is at most k. But unfortunately, this analysis is tight. So there are examples where you need really a tree of height k to make the separation. If you just look at unit vectors, if you have k unit vectors in k dimensions, with a single threshold cut, you can separate only one of them. So you need k cuts, and this tree is like a kind of caterpillar-like. So this bound cannot be improved. And also in this paper, they provided a lower bound. So they showed an instance, or like a family of instances, in which any explainable clustering is at least log k times worse than an optimal clustering. Which means that we have an upper bound and lower bound for the price of explainability, but they are quite far from each other. It's k and log k. And this is what we knew at the end of 2020. Then in 2021, people from Chicago came up with an algorithm which I will call in this talk a TCS algorithm. It improved the bound. Later I will tell you how. Also in 2021, me and my colleagues from Lausanne, we independently proposed the TCS algorithm. And in the same year, people from Google Research in New York, they also proposed the TCS algorithm. So these 3 papers appeared on arXiv within 4 days. How is it possible that 3 groups of researchers independently came up with the same algorithm? Well, I think it's because the algorithm is simple. It's actually simpler than the original one. So in the original algorithm, whenever we were making a cut, we were selecting a minimum cut. So we thought, instead of a minimum cut, let's take a random cut. I can give you some intuition why this idea was natural. So the problem with taking the minimum cut was that at each level of the tree, you pay opt, but the tree can have height k. Now the intuition is that if you take a random cut, you would split the points roughly in 2 halves. So your tree will be of height log k. This intuition is not true in the sense that you can still get a very deep tree using random cuts. But it is true. The intuition is true in that sense that by taking random cuts, you get better bounds. You can prove better bounds on the price that you get. But I'm not going to go into the proof today. Let me just explain a bit more what exactly I mean by random cut. Oops. Okay. So here's the initial clustering. I draw a bounding box around my centers. It doesn't make sense to make a cut such that all points are on the same side, all centers are on the same side, so it has to lie within the bounding box. So this is the bounding box, and I pick the dimension proportionally to the length of the boundary of the bounding box in this dimension. So I will pick this one with probability L1 divided by L1 plus L2, and the other one with L2 divided by the sum. And then I make a cut uniformly at random. And now, let's say for this part, I update the bounding box, and again, choose the dimension, and then choose a random threshold. So that's the algorithm. The algorithm was the same in all three papers. They had different analysis, and they proved different bounds. They were all around log k. Actually, we proved the worst one. We proved log squared k. The other two guys proved log k, log k, and also something depending on dimension, if the dimension is small. So at the end of 21, the question about explainable clustering had this gap between log k and log k, log k. So it was almost settled. And 2 years later, Ola with people from CMU settled it completely. They proved an upper bound of O of log k. It's just a different analysis of still the same algorithm. So this algorithm is the answer to the problem. This sounds like there is nothing more to do about explainable clustering, at least in this formalization. It's not necessarily true. There are some problems left. So this was about k-medians. For k-means, which is maybe a bit more natural clustering objective, we still have a gap. The gap is between k and k log k. Another question is, what if we allow more cuts, more dimensions in a cut? So you can argue, I'm not a big fan of it, but you can argue that, okay, having a linear combination of two dimensions, it's still something kind of easy to grasp. It's at least not 500. So maybe by allowing more dimensions, we could have a smaller price. We don't know that. And another question would be, maybe we can have some assumption about data that allows us to show smaller price. So like this lower bound of log k is kind of like a very artificial example. So maybe for natural data, you can explain it with paying a smaller price, because like you can approximate k-means or k-medians very well. So if I tell you, okay, and you on top of that, on top of this 1 point something approximation factor, you also pay like log k to get explainability, well, nobody would use it. So it would be nice to find a setting in which you can reduce this price below log k, and that's the question I particularly like. Let me stop here. Thank you very much.